This lesson is about systems of equations, special cases. Now there are three ways to solve for a system of equation. Again, a system of equations is where you have two linear equations that intersect or that have a relationship with one another. Generally, there are three ways to find that relationship or that intersection point. The three ways is one, to graph them, graph the two lines on the same coordinate plane. The second is to use substitution, which is another lesson, video lesson on that. And then the third is using the elimination method. There's also a video lesson about that. This video lesson, however, is a special case. And this is what it's talking about. Usually our answers for a system of equations, solving for it, is usually a ordered pair, a point where two lines intersect. They intersect at one point. However, there are times, specifically two times, when you could have something other than that solution. It occurs when using either method, substitution or elimination, or even graphing, which is mentioned here, and all the variables cancel out. Your answer will be determined by what remains. Either no solution, which means that the two lines created parallel lines, or infinitely many solutions, meaning that both equations are exactly the same line. Here's an example. Notice this right here. You have x plus y equals a negative 18 and x plus 6y equals a negative 36. Notice that creates two parallel lines when you graph them on a graph. If they're parallel, they'll never intersect. So your answer then has to be no solution, because there is no place that those two could intersect. Now, my question is, what does it look like if you were to use substitution method on these two this system of equation to find that intersection point? What would it look like? How would we know that there's no solution without graphing them? Well, let's do that. Let's take this first equation, x plus 6y equals a negative 18, and let's solve for the x. So in order to do that, we move the 6y over to the other side by subtracting 6y on both sides, minus 6y. So that leaves us with x. The y's, that would cancel out there, and it would look like this, negative 6y minus 18. Alright, x is equal to a negative 6y minus 18. Now let's take the value of this and substitute it in the place of x in this other equation. Thus the substitution method. So you would have parentheses, negative 6y minus 18, now that is where the x would be, plus 6y equals negative 36. Notice I took this equation here and I rewrote it, except I replaced where the x would be with the value of x. Alright, let's drop the parentheses. Negative 6y minus 18 plus 6y equals a negative 36. Okay, notice my 6y here and my positive 6y here will cancel out because one's negative, one's positive, leaving me 18 is equal to a negative 36. Now, what's happened is all my variables canceled out. I have no variables left except, and all I have is constants, negative 18 and a negative 36. Now, let's look at it. Do these equal? Are they the same number? And the obvious answer is no. Negative 18 does not equal negative 36. Therefore, this cannot be a correct statement, for these do not equal. So the solution for this system of equation has to be no solution. And that's how you know. If both sides of whatever's left over doesn't equal, then it's no solution. Now let's look at an alternative problem, but let's use a different method. Let's use elimination to solve this one. Alright, here's your two equations. 10x plus 7y equals 1, And negative 20x minus 14y equals a negative 2. To use elimination, we would need, let's move this over a little bit. We would need to get the same coefficient, different sign. So this would be the, let's see, either one would be fine. Let's just do a 2. Let's multiply this top by 2. What that would give me then is 20x, positive 20x, and a negative 20x. So let's do that. And I'm going to rewrite it right here below. So I have 20x, and 2 times 7 is a positive 14, y equals 2. Alright, now notice, negative 20x, 20x, so I know at least one of my variables cancel, so let's add these two here together, and we get negative 20x, positive 20x, that goes to 0, so I get 0 here. Negative 14, positive 14, that goes to 0, so that cancels, so that leaves me with the 0 on this side of the equal sign. Negative 2, positive 2, that's a 0. Now look, all my variables cancel out, and all I'm left with is 0 equals 0. Is that a true statement? Yes, the statement is true, 0 equals 0. So then this one would say that it is not a no solution because both sides equal. What it is many solutions. What it says is that these two lines are exactly the same line. Now how do I know that? Well, let's rewrite these and let's look at them. You have 10x plus 7y equals 1. Let's look at the next one. You have negative 20x minus 14y equals a negative 2. What if I divided every term in here by a negative 2? What is negative 20 divided by negative 2? Should be 10x. What's negative 2 divided by, or negative 14 divided by negative y? I'm sorry, what is negative 14 divided by negative 2? That's going to be a positive 7y. And what is negative 2 divided by negative 2? Well, that's going to be 1. Look, both equation is the same thing. All that has happened here is that they took this original equation and multiplied it by a negative 2. See, if I take this and multiply everything by negative 2, I get 20x, negative 20x, negative 14y equals negative 2, which is what I began with. So, when you have a situation where all the variables cancel out and both sides are equal, your answer is many solutions because those two equations are the same line. Okay, that concludes our discussion on systems of equations, special products, or special solutions. Special cases, I guess I should say.